Hi, my name is Kianna Olson, and I'm presenting on my research of reverberation mapping NGC 2617. The group I'm working with at the University of Wyoming is the Maha Group, and it actually spans multiple different universities and institutions. And Maha stands for Monitoring AGN with H-beta Asymmetry. In this project, we're doing reverberation mapping using the Wyoming Infrared Telescope, otherwise known as WIRO. And we've been observing for over 3 years on this project and have observed more than 53 different AGN. So starting off with what is an AGN, which stands for an active galactic nuclei. So as far as we understand, all galaxies have a black hole at the center, supermassive black hole. And some of these black holes are actively accreting into their accretion disk around them, which is this luminous disk. And so those that are actively accreting, actively consuming, are termed active, thus your AGN. So the other term you're going to need to understand my research is reverberation mapping. Reverberation mapping relies on the fact that light travels at a constant speed. So if our accretion disk on the black hole flares or dims, the change in the light from the front that's closest to us is going to reach us on Earth before the light from the back of it. So we can measure the difference in that by following its light curve of looking for a peak or a dimming, measure the amount of time between that, and that gives us our time lag. Other piece of information we use is the Doppler effect, so that's your red shift and your blue shift. And we can use that to determine the orbital velocity around our black hole. And from those two pieces of information, we can combine them to determine the mass. For my particular object, NGC 2617, that I'm working on, before we started this project, we knew from Frosnow et al. 2017 that it had been labeled a changing look AGN, that they had determined that they had a time lag of about 6 days on this object and had calculated a mass of 32 million solar masses. For our new data, we found the time lag for ours to be about 7 days and our black hole mass to be 58 million solar masses. Now, that might seem like a really big change in number, but actually it's just a little bit of a percentile change, being how big of a number we're already dealing with. And there's a likelihood that the data we're dealing with might be more accurate, being that we have been observing this object far longer and with more consistency. The other new piece of data that we have to add is the bump here, the asymmetry that we've been monitoring. This bump used to be on the left side of the H beta, and during our time of observing, we've watched this bump grow and shrink and shift. So we're hoping in the future that we'll get to see it shift to the other side. I'd like to say a special thank you to Bao Dong Wei and many other members of our research group for helping with calculations, code, and observing. And that is my research in a nutshell. I'm happy to answer any questions. Thank you.